So thank you everybody for joining this evening. And this is a professional training on the mitochondrial laboratory that we work with, MMD, and it's in Germany. We are the Academy of Nutritional Medicine, AUNM, as I'm sure you know. And so I have got a presentation planned, but we'll leave ample time for questions at the end. So this first bit is being recorded, and none of your names will be visible on the recording. And afterwards, when I've finished the presentation, we'll stop recording and you'll be able to open up your microphones and speak, or also pop questions into the chat at any time you wish, or the Q&A. So I'll just switch off the chat for myself here and go into my slides and open up the share so that you can all see my screen, and I'm enlarging it to slide view. So the mitochondrial testing that we do here at AUNM is really very special. We're very, very glad to have it. Some of you may remember Acumen, which stopped doing mitochondrial testing at the beginning of the pandemic, and we had known about this laboratory, an excellent one in Germany, for many years, and we felt at that time it was the right moment to introduce it. And they do testing of a large number of different parameters. So I'll go through some of them today, but probably not have time to cover all of them. There are lots of recordings on our website, aunm.org, under mitochondrial testing, which is the link you can see here. So for anybody who's new to this, please do go there and have a look at any of those webinars that are up there. So we'll cover this evening the ATP profile and the mitochondrial health index primarily, and as many of the supplementary biomarkers as we have time for, whereby, as I mentioned, there are longer webinars up on the website. So the ATP profile, it's important to say, is the mitochondria at rest. And then quite special, which I don't think was something that Acumen used to do, the health index, or the performance of the mitochondria, is the mitochondria under pressure. And the Seahorse XF, which is a very advanced system now used all over the world for mitochondrial testing. Over 8,000 peer-reviewed studies have been performed using the Seahorse XF for the mitochondria. That has a special way of standardizing pressure so that you can see the difficulties along the mitochondrial chain and where some of the blocks might be. So I'll first of all describe a little about the mitochondrial ATP profile. So this is the first page of a 5-page report that comes, and it shows you the capacity of the mitochondria to produce ATP, the capacity of glycolysis to produce ATP, because of course the precursors to the mitochondria along glycolysis also produce 2 ATP. And then the total of those two makes up the total ATP. So people often say, well, how come when I have very little mitochondrial and glycolytic ATP capacity, do I still have a slightly better total ATP? But it's because the two of them together, the body is able to sort of grasp production from wherever it can. And at rest, often that's even in the green zone, if the mitochondrial and glycolytic ATP are ailing a bit. And then the reserve ATP capacity shows you how well the body is able to conduct what's called nutrient sensing, in other words, to sort of grasp the various different precursors to ATP from wherever they are in the cell. And of course, the body is extremely intelligent and can do that. It's a particular pathway called the adenylate pathway that uses various different components as an alternative way of producing ATP. But here you can see that the patient in this particular example was ailing along his ATP capacity pathway for the mitochondria and glycolysis, as well as reserve capacity. And the total ATP was just a little bit better. So this is using femtomoles per cell, which are tiny, tiny little units along the left and percentages along the right. And you'd expect at least 80%, ideally, for these two here. And for this one as well, ideally at the bottom, the reserve ATP capacity and the total ATP should be 1.4 to 1.6 ideally. It's also not good if it's too high because this is at rest. And if it's a bit like a car engine revving at rest, if it's going at a rate of knots while at rest, then that's a sign that much too much ATP is being used and you'll have nothing left under pressure. So that's why we have a discrete section in the middle there that's ideal. And if the mitochondrial ATP is as low as this, 0.4, where it should be above 1.4, then obviously you've got a problem. That's just not going to be enough, even at rest. This is the equivalent of the patient lying on a sofa and not doing anything. And 0.5 is obviously not within the range of above 1.4 either. So that's about a third of what it should be ideally. And that's reflected in the 63% here too. And it's always, by the way, a percentage of the total. So 50 is 50% of 0.4 is 50% of 0.8. So that's why you've got 50% here. Sometimes people get confused over the figures because it's not a standard figure. It's related to the patient's own total ATP figure here at the top. And so going on to the next page, we have a description of how each of those figures are calculated. And so I won't go through that because I did talk through that in some detail. I'm hoping that all of you understand that ATP means adenosine triphosphate, and it's the currency of our cells. I'm sure you all do. And so if you need any further detail on the terms I'm using, especially if I abbreviate them, then just please put that into the chat and we'll resolve that right away at the end. The next page also explains a little bit about how these figures have been calculated. And the last one is talking about the reserve ATP capacity. So I don't think it's necessary for me to go all through that, but if you read it through and then have questions, please obviously get back to me or to us. So reasons why the ATP profile at rest may be struggling are that if you can't, I mean, there are hundreds of reasons, to be honest, so it's not appropriate to sort of make things too simplistic. But we did have a presentation last Tuesday where the professor of the laboratory, Professor Koenig, and I talked about some of the approaches a therapist might want to take. So I do suggest you look at that. It's the last one. It's in the top left corner that's been put under mitochondrial webinars. And we did say that if the patient has insulin resistance and is unable to even allow glucose into their cells to begin going down that glycolytic pathway to produce the precursors for the mitochondrial energy, then of course you'll have a problem and you'll notice ailing glycolytic ATP capacity. And so insulin, as you can see here, needs to get into the cell via the GLUT2 or 4 receptor, depending on which cells in the body you're talking about. And just recently, we had an entire weekend about the mitochondria that the NMI ran in the UK. And Dr. Pizzorno, who'd come over from the States for that, said that their figures had shown that 95% of the US population had insulin resistance to a degree. And so that would be a very clear reason for difficulties along even the resting ATP profile. And so in that other presentation from last Tuesday, we gave a few further tips on what you could look at as a therapist. And of course, the different tests you might want to do, you'll know about, like measuring insulin and glucose and HB1C and so on. So I'm just going to move on now to the next chart, which is that if you want to get the glycolytic precursors into the mitochondria, which is this yellow ring here, then along the pyruvate pathway to get in, you need magnesium, various B vitamins, and alpha lipoic acid, among other things. You know, everything in the body, you know, is a sort of orchestra that requires a lot of different synergistic components, but particularly B1, B2, 3, and 5. Ideally B5 in the form of pantethine, which is the fat-soluble form of B5. Dr. Klinghardt has been emphasizing that recently. And similarly B1 in the form of benphthiamine, which is the fat-soluble form of B1. If it's fat-soluble, as well as being water-soluble, which the B vitamins generally are. I mean, the B vitamins, as a standard, are water-soluble, but there are ways of making them fat-soluble as well. Then they get through the membrane and through the blood-brain barrier a lot easier. So be looking out for the fat-soluble forms of the B vitamins if your patients are having problems along the glycolytic ATP capacity pathway. And ALA, alpha lipoic acid, is excellent as well, in the R form particularly. And then magnesium. That's important for all pathways. You can see for the fatty acid pathway, we also have magnesium and B2. So if your mitochondrial ATP capacity on this ATP profile is stronger than the glycolytic capacity, which can happen, and then patients are always surprised, the reason actually is that their fatty acid pathway is working better. And the mitochondria love fatty acids as a fuel. You can get far more calories from, 1 mole of fatty acids than you actually can from carbohydrates, as you'll know, 9 rather than 4. And they can produce far more ATP from fatty acids than they can from carbohydrates. So the entry point for fatty acids into the mitochondria requires, as well as magnesium and B2, carnitine. And of course, make sure that your patients have carnitine if they're having problems along that pathway, i.e. the ATP mitochondrial capacity. But if that seems to be working better, then it means that their carnitine is doing well. Often that's a meat eater, or at least it's somebody who's not a vegan or a vegetarian. Vegans or vegetarians can have real problems getting enough carnitine, as well as other nutrients, as you'll all know. So that's interesting, I think. And there are other reasons why there might be problems with that pathway, but we won't go into those now. They're more fatty acid oxidation disorders that you can be born with. So now we'll look briefly at the mitochondrial health index. This is the key test that if your patients want to sort of start doing this kind of testing, but their funds are limited, then please do this one over the ATP profile, because most patients that we tend to have will have a degree of CFSME alongside whatever else is going on, whether it's fibromyalgia or POTS or whatever. And so making sure that you're able to test their mitochondria under pressure is always that much more valuable, though it's very useful to be able to see the ATP profile as well, as we've just discussed. So this is the top page of an 11-page report, the Mitochondrial Health Index, abbreviated MHI. And there's a lot to say about this. So every time you do this test with us, I'm always there to help you interpret it. And if it's the first time you do it, for example, we're very, happy to invite the professor to be there as well. And also, if we have interesting points where I can't, give you the full answer, then we'll invite her in or send her an email and ask for her opinion. So we have a very good connection with the laboratory and can get fairly swift answers. So this was, as you can tell, a patient who was having great difficulty with their mitochondria, even under pressure. The first place that the professor tends to look is the non-mitochondrial respiration. That's this parameter here. And here you can see that it's not over 90%, which it should be, because it says here the target value for the non-mitochondrial respiration, which is oxygen, i.e. how much oxygen is getting into the mitochondria and how much is being used outside the mitochondria. Non-mitochondria should be less than 10%. And here it's 32% here. And then because 10% is being wasted on a proton leak, though a little bit is allowed, that's why it's still in green, but 10% is right at the outside of what's allowed. It's that absolute top value, so it's really too much. So 32 plus 10 makes 42, so only 58% of the oxygen is actually getting into the mitochondria, and it should be over 90%. So that's too little. And also we can see that the base turnover of the mitochondria is very high. Do you remember I said with the ATP profile that if you can see a lot of ATP being used at the baseline over that 1.6 femtomoles, that's too much. It means the mitochondria is already ticking over like that car that's sort of booming away on the street but not even moving. That means that there are either too many mitochondria in that particular cell and they're all eating up ATP and yet unable to really be fully functional, or that something else has gone wrong. So that's much too high here. 100% at base means you have nothing left as the reserve, and that's why we have a 0 here. So a lot of this is a complicated calculation that one can talk through in greater detail, but overall, the potential maximum oxygen consumption rate is only 22 when it should be over 500. And obviously this is an extreme example. We're using this with the patient's permission, and we do know the severe condition the patient was in. Your patients, I'm sure, won't look like this, but 22 means that actually over here, the reserve respiration capacity, in other words, how much the bellows, if you think of the mitochondria as a bellow that you can expand and put under pressure so that you can really do that marathon run or go on that big shop or whatever you need to do, that's 0 here. In other words, the patient was bedbound, and it should be over 400%. In other words, the patient should be able to expand their mitochondria 4 times when they need to. And you can see from this that the patient will have huge post-exertional fatigue if they try to do anything. They'll probably have to rest for about 3 days. That's how long it takes for ATP to be built de novo. In other words, from the beginning, when you have to put D-ribose together with all the other components to make ATP right from the beginning. It takes about 3 days. And that's something you may recognize in your patients. They just do a little and they collapse for 3 days. So here at the bottom, you can see a strong preference for anaerobic glycolysis, which means production of energy along the glycolysis pathway without it getting into the mitochondria well. Anaerobic means without oxygen. So that's reflected on the second page of the test in a more generalized way. Obviously, you as the therapist will probably put this together with other tests that you have of the patient and be able to explain a lot more. This tells you that the patient has increased formation of oxygen radicals in the cell. If they have increased formation along the electron transport chain of the mitochondria, it'll have a yes here. This particular example, it was a no. What function they have along the electron transport chain, which is within the mitochondria, you have the Krebs cycle and the ETC, the electron transport chain. So the ETC is where you get most ATP if that's working properly. It's a very complex process, so lots and lots more to say about this. But here it's yes, restricted function, limited number of functionally intact mitochondria. That's an indication that it's really worth checking the mitochondrial mass. In other words, doing the number of mitochondria to see, do they have too many or too few? What's going on there? And so on. So this is a useful page, but there are, as I say, another 9 pages to this test, and I'm very happy to send an example full test to anybody who would like one. So when you do several tests, we're very happy to put them next to each other. This is an example of 3 tests, and you can see the gradual improvement. This was 2020, 2021. We've got a lot more green developing, no more reds. You know, if you looked at each individual parameter, you would see that there was, in most cases, an improvement. So that was actually somebody developing improvements post-COVID. So the supplementary biomarkers are, for example, the mitochondrial number compared to the nucleus. Now, cells only have one nucleus, whereas they have many mitochondria, and the mitochondria have their own DNA. So you can work out using the technology that's available to us nowadays how many mitochondria there are in the cell, or at least the ratio of the mitochondrial DNA to the nuclear DNA. And this is a rather complicated chart, but it's basically the genome of a mitochondrion, showing what parts of the genome are responsible for complex 1, 2, 3, 4, and 5. Actually, 2 isn't in there, but 2 is a very specific complex that's not really involved in producing the energy. And so what you can do from that is work out a number. And it should ideally be between, in these particular cells, we're using peripheral blood nuclear cells. They PBC, peripheral blood. I've completely lost, I've got a complete blackout about the type of cell we're using as a name, as an abbreviation. But they're peripheral blood cells which are not erythrocytes. In other words, they're the immune cells, because you've only got 2 types of cell that you can pull out of the blood, and we're doing blood tests. You can only use the erythrocytes or the immune cells, and erythrocytes don't have any mitochondria, so they would be useless to use. So we're using the immune cells, very specific kinds. They are being sorted and selected at the laboratory because neutrophils, for example, don't have the same number of mitochondria as others. So it's about 200 to 250 that we're looking for in those types of cells. And this patient has green, in other words, 202. But on the next chart, you can see that they have far too many, over 1,000, and that is in the red. Now, what that means if you get that number, is that the cell is trying to counteract the lack of energy by increasing the number of mitochondria. So that would be a reason for the 100% baseline that we saw on that MHI just now. It's like, hundreds of children in a classroom that's only for 20. You just can't cope with it. They're utilizing everything that's there in terms of resources, and there's no proper production of the work you want to achieve at all. And if it's too low, which is in this example here, only 115 when you want your 200 to 250, then the cell is unable to counteract the lack of energy by increasing the number of mitochondria. So if it's too many, then mitophagy is called for, ideally, which means pruning the number of mitochondria, a bit like you'd prune a bed of roses, getting rid of the dysfunctional ones back to the right number. And if you have too few, then something called mitobiogenesis is called for, which is increasing the number of mitochondria. And sometimes the body can do that itself, and we have a test that shows you whether the organism can or not. And sometimes you have to just push the patient a little bit in order to get their cells doing that. And we have a whole list of things you can use for mitobiogenesis. So let's have a look at those tests you can do to see how well the patient can do it themselves. Now, PGC1 alpha is central for producing new mitochondria, and it's this that we measure. It regulates mitochondrial biogenesis, as well as doing a lot more. So there's lots and lots of information in this article, as well as thousands of others. And so the test is called PGC1 alpha. It's the test of how well that is working in the patient. And if it's low like this, and the patient has a low number of mitochondria like we've just seen, then you would want to support their mitobiogenesis. And here it's barely detectable, which indicates extremely low new mitochondrial formation. If the patient has masses of mitochondria, like in that over 1,000 that we saw, then it's normal for the body to be regulating appropriately, to be keeping the PGC1 alpha low, because the body has detected it's not needed. So it's always necessary to see this in relation to the other one, i.e. the mitochondrial number. So the other test we can do, and this we can do as a finger prick test as well, if you want to sort of check on it regularly, like once every 3 months or 6 months or whatever, is a test of oxidative stress. How much the mitochondria have been affected by ROS, which stands for reactive oxygen species. And you can work this out because parts of their genome get sort of lopped off if their mitochondria are actually being compromised by reactive oxygen species. The lab uses a very common deletion called 4977 base pairs. If you look this up in the literature, you'll see lots and lots of articles about that. It's very well researched. And if that's been deleted, then the mitochondrial genome shrinks. In this example, for example, it's got far less than the over 16,500 base pairs it has. It has only 11,500 base pairs. So as it shrinks, it becomes unable to produce ATP. And this is explained here in the next chart, last sentence, which is directly from a scientific article on this, that the deleted region, which encodes very special sections essential for producing oxygen metabolism in the mitochondria, if that's being deleted, this can cause complete failure of ATP production in the mitochondria affected. So you want to catch that that's happening, and you want to reverse it. And it can be reversed. we would never really want to test anything genetic that cannot be reversed, and this can be backpedaled. So here you can see an example of how it's enhanced. It's in the red zone, and this indicates oxidative stress and damage to mitochondrial DNA. So one of the things you can do is to look at the NRF2 level in the patient, which is a transcription factor that is a master antioxidant regulator, again, among other things. You know, it does many, many things in the body, but one of the key things it does is regulate our antioxidants, and that's tested using the test called NRF2, and here it was not detectable. So if you've got this test alongside the mitochondrial stress test that we've just looked at, then this is a sign that you definitely need to give your patient antioxidants, and ideally specific ones that will help their own oxidases, catalase, superoxide dismutase, glutathione peroxidase, that will help their own antioxidant enzymes to work. So the test of mitochondrial oxidations, as I mentioned, can also be done as a finger prick test. That makes it a lot easier. The patient can do it at home, and it has a very long life, so that doesn't have to reach the lab within about 48 hours like the other tests that are done from fresh blood. That can travel almost as long as you like. It's very, very stable finger prick paper that we use. So pyruvate, this is probably the last one I'll go into in great detail. Pyruvate is, well, when I say great, in the detail we have time for, pyruvate is the pathway into the mitochondria. You'll remember that. And if you have a lot of lactic acid forming, you can see on this picture, that's because the pyruvic acid isn't getting into the mitochondria. It's being backpedaled into lactic acid. And lactic acid that builds up in the cells causes pain. It's a bit like what marathon runners feel at the end of their marathon run. You know, great pain in the muscles. And so if you have a patient with fibromyalgia, often that will be accompanied by mitochondrial distress. And you can tell from the lactate pyruvate ratio, or we often call it lactate pyruvate index, how well the patient is able to ferry fats and or carbohydrates into their mitochondria. In other words, it gives you an indication of the fuels the mitochondria are able to use. So here it explains the higher the value of lactate compared to pyruvate, the more glycolysis is occurring. And you can see here that the numbers do correspond well to, well, I mean, it isn't a validated test. The numbers do correspond well to how efficiently the various fuels are getting into the mitochondria. So this is what the test looks like here. Again, it's a couple of pages. The second page explains how it's been done. You get the lactate pyruvate index in dormant cells. That's the cells at rest, like in the ATP profile. And then you get the lactate pyruvate in activated cells, which is like the MHI, where the cells are under pressure. And you can see here that the number is higher, which means worse. It's higher when the patient is running or doing their big supermarket shop or whatever. In other words, here, the cells are primarily metabolizing carbohydrates and partially converting them to lactate. You can see what the 1.61 means by looking at the index here. That's this here, between 1.2 and 2. And the 2.43 has gone well above the max. The cell is primarily using carbohydrates and preferentially converting them to lactate. Here it says about 80% of them. So this means that fats are not getting into the cell. Not well anyway, when I say into the cell, into the mitochondria. And so there are certain things that you can do to encourage that, because you really, really do want the mitochondria to be able to process fats, which are such a prime source of energy. And that's why the ketogenic diet is often lauded above all others. But it's important to really have a balance and to make sure that your mitochondria are able to grasp out for whatever is available and utilize it. You're not always going to have, the same diet available. And the I don't think we have a lot more. There is another test which some of you have done, I know, called the mitochondrial fuel pathways, which gives a bit more detail about that. And that is here on this order form under M12, but we don't have time to talk about that today. So you can see here the different numbers given to the different tests and the prices. Of course, if you're a therapist, do ask us, because there will be, as there always is, a slight difference between the therapist price and the patient price. And so these are all the different tests. We have gone through most of them, actually, just not those last two, 11 and 12. This is a test of telomere length that can also be done. That's not really a mitochondrial test, but it's an interesting one, because that can be matched to the patient's age, and then the patient can see whether they've actually got, a lot of sort of telomere length left, or whether it's been overused. There's a lot of science to that that's fascinating, but we won't go through that today. But that is possible as a finger prick test. You can see on this form here, we can do the stress test, which is the first one here, as a finger prick test, and also the telomere length, that's number 8. These two, M6 and M15, tend to be less useful unless you've got other tests of those live blood kind to compare them with. But do consider doing FP1 or FP8. So a few more sources here if you want to look up the seahorse technology. Sorry, there's a mistake in the number here, which I had just upgraded from 7,200 to over 8,000, because I'd found that on the web page that's linked at the bottom, but I made a mistake there. I forgot to delete the 2. And so that's all that we'll go through today. Thanks very, very much.